Hello viewers and welcome to another episode of Space Science with Python. In today's session we will start again with some coding and I will talk about the size distribution of near-Earth objects. So first of all we created a small database, we talked about the scientific purpose or the project we want to do, and now we have a lot of data in our database and now it's time to dive into the data. So today we will talk about the size distribution and the bias effects, and next time we will talk about the orbital elements and the orbit distribution. And I will also tell you why we are doing this, because it's not something we do just for fun. It's also very important to keep these things in mind when we are in the future also considering theoretical models of near-Earth objects. Now you may recall that we do not have any size distribution in our near-Earth object database, but we have something called the absolute magnitude. So the absolute magnitude is a simple value. It's written down, or in scientific papers it's written as h. And the absolute magnitude can be derived from the apparent magnitude. So you may remember from the older videos, the apparent magnitude is the brightness of an object in a logarithmic scale, where the brightness is negatively correlated with the absolute magnitude, which means that a larger or bigger value corresponds to a fainter object and vice versa. So the absolute magnitude, on the other hand, is an intrinsic parameter, so something that is completely independent of the observational status in a way, because first of all, the absolute magnitude is related to the size of the object, but it's also defined a little bit with I would say a unrealistic or geometric impossible situation, because the absolute magnitude is the magnitude of an object where the distance of the object to the sun, so delta r, or let's say delta d for the distance, the delta distance to the sun equals 1 AU, and also the delta to the earth corresponds also to 1 AU. And this is geometrically not possible, but for mostly in the near Earth object, comet and comet science, it is a used parameter. And with this absolute magnitude we can compute the size of an object. And in the future, we will also talk how we can derive or compute the absolute magnitude. So there are a lot of equations and so on. We will also talk about the apparent magnitude. Just as a small spoiler, the apparent magnitude depends on a lot of factors. So for example, we have here the planet Earth, we have here the sun, and we have here somewhere the near-Earth object, something like this. So we have like 3 different distances. We have the distance from the sun to the Earth, we have the distance from the sun to the near-Earth object, and we have also the distance from the near-Earth object to the Earth, as well as something called a phase angle, so the angle of the object between of the 2 vectors, as I've drawn here. That's now, it can vary between 0 degrees and 180 degrees. So if it's here in the line, so let's say just marking it with a red X here, we have a phase angle of 180 degrees. If we have the object here in so-called opposition, it's 0 degrees, so something like a full moon or full NEO. And of course, these kind of geometric things also correspond to a illumination that can be seen as a not as a crescent moon, but in a way a crescent NEO. But this is something for the future, so we will also compute the apparent magnitude in the future, so don't worry, but we are not going to do this today. Today we will use this parameter h to compute the size of a near-Earth object. So how can we transform this value h now to the size? Well, there is an empirical equation, and it's quite simple. So it computes the diameter of an object or asteroid. Let's call it diameter NEO, and this is equal to 10 to the power of minus 0.2 times h, so the absolute magnitude, you see it here, divided by the square root of a, we'll just tell you in a moment what a is, times 1,329 kilometers. So or let's say the diameter is now given then in kilometers. So this first part here has no dimension at all. So there's no dimensionality, so no physical unit. Here we have kilometers. So all in all, we get something in kilometers. And this value A is something called the albedo. And the albedo varies between the values, these values 0 and 1. And it provides, or is simply a value that indicates the reflectance of an object. So let's say an object with the reflectance, or with the albedo 0, does not reflect anything at all. It's pure pitch black. So like a black hole, there is no reflectance at all. And 1 means that it's reflecting all the incoming light perfectly 100%. I told you in the in the past videos that, for example, the reflectance of comets is even lower than from asteroids. So it's very, very dark, darker than coal. For asteroids, we have a varying range of values. So, for example, the asteroid, the NEO 433 Eros, has an albedo, I think, of 0.25. So, let's say it's quite reflective. But for most objects, we do not have the albedo values, and there we assume a default value. And this default value, let's say at a depth, is simply 0.15. So, if you want to work with size distributions or so, you can simply use this 0.15. That's quite okay. We will just write this equation now in the Python code, and then you can also play around a little bit and see how the size distribution changes with different albedo values. So the absolute magnitude is known, and the albedo value can be changed. You can create, for example, a two-dimensional plot. So, for example, what you can do is you can make a plot where we have here, for example, the absolute magnitude, we have here the albedo, and then you can create a color plot where the color indicates, I don't know, the diameter or something. So some kind of distribution should be possible. So this is maybe something like a small homework for you to create this kind of two-dimensional, or let's say three-dimensional plot where you vary the absolute magnitude and the albedo and get the corresponding size. Now it's time for some coding, and for this video I prepared a small project, a script, notebook script. Quite simple. First of all, we are importing the modules. In the second cell, we are opening the NeoDice database, and then we are in cell number 3, we are obtaining the data from the database. And the database is quite small, only a few kilobytes or so. So we just read everything from the main table. So select all from main. We use the connector here, and we do not use SQLite 3, but we use pandas. So it's pd.readsql, and then afterwards we can simply close the database. So we get here a data frame, and this can be shown now here in cell number 4. And this is something we have we talked about in the past. Yeah, we see here the name, the epoch, the corresponding orbital elements, and there we see also the absolute magnitude. So for example, for Eros 433, the absolute magnitude is 10.87. Doesn't give you now any feeling or idea what the size is, but we will compute it now just in a second. So let's scroll down. We define our small function here. So the function here you see in cell number 5, we have we declare our units. We have here also a small doc string, which is also important. We will use these functions also in the future, so for recycling purposes. And there we have a one-liner for our function itself. So let's simply execute this command, and then we can move to cell number 6. In cell number 6, we are doing a very simple operation. So we have here a list comprehension where we compute the size of the NEOs in this for loop within this list comprehension, iterating over all absolute magnitude values, and then we round the values by 2. So the result is given in kilometers, so we round down to tens of meters. So yeah, that's fine, I think. And this is something we can now work on. Also, let's print down some statistics. We take a look here, and now we see here our resulting statistics. We see here the known minimum, so the minimum value, the maximum value of the diameters, and we see 0 kilometers and over 300,000 kilometers. So this is really huge. I don't know, this would be an NEO of a tremendous size, so a little bit frightening, but don't worry, we will talk a little bit about data quality just in a moment. Also here with the mean and with the median value, so also a little bit strongly asymmetric distribution. A little bit strange, the values, right? So let's take a look at command number 7, where we are sorting our neo data frame by the absolute magnitude, and we simply print the name and the corresponding absolute magnitude here in cell number 7. And we see that, for example, for this very small object, no, not small object, but yeah, it's probably very small object, we have a very weird absolute magnitude as minus 9.99. So, I mean, it's very likely that it's a very small object. It does not have any name, no declaration or something. Okay, it has a declaration, but no any name. And a NEO with a size of 300,000 kilometers would for sure have a name, right? And the absolute magnitude of 9.99 or minus 9.99, it indicates that this is an error, a value that is not really correct. Yeah, so this is really strange. And this value here, as I said, a smaller value corresponds to a larger result. Very strange. So this is most likely resulting, or a value that is not 100% correct. Also, the second one with 0.17, this is also extremely unrealistic, because if you are doing some research, you will find an asteroid called 1036 Ganymed. So Ganymed, not the moon of Jupiter, but it's also an NEO floating around. I think it's an Aten or Apollo, something like that. It's not an Earth crosser, so don't worry, because this is a realistic value here, and Ganymed has an approximate size of 35 kilometers. So quite huge NEO. Again, it's not Earth crossing at all, so don't worry. And this is the largest known near-Earth object. So which means that these two values here, they are probably not correct. The same thing applies also for the very last two ones. We have here 99.9 and 99.9. I mean, okay, now with rounding errors, we got 0.0 kilometers, but this would like correspond to just a few centimeters, right? I mean, yeah, we can simply make a quick computation. So we take this, let's remove this here first. We just use 99.90. We use the standard or the default value for albedos that was defined here in the function. So let's see, what is this in kilometers? It's a dust particle. It's very, very small particle. So this is quite unrealistic, and we should stick here with our sorting here and ignore the last NEOs. But we will keep them though also in the future, because they have orbital elements, and we want to use all orbital elements, and we will see if there are also some error as well or not. Now, talking about the size distribution, let's do a simple plot, a histogram, right? Something that we did also in the past for our comets. So this is something that we already did and understood in the past. So we can now reapply things we already learned in this more generic videos and apply them now for our NEOs, where we simply make a distribution of the sizes. And we see here in small bins of what kind of size did I choose? In 10-meter bin sizes, so I'm not using a kernel density estimator or something, so simply a histogram. We see here that we know, or the number of NEOs increases for smaller sizes, and then we have an immediate drop. And this drop it's probably very unlikely that there are no NEOs. They are simply very difficult to discover. So very small objects are extremely faint, and only if we have a very geometric, a very good geometric situation, we can observe them. So something like they are they have a flyby between, I don't know, moon and Earth or something. So very strange that we have here the small gap. Remember what our task is. We want to define in the long run an observation strategy for a telescope. And now we try to understand the data first, and we see that there is a gap of smaller NEOs. So later we will use a theoretical neo-population model, and we will focus on the very small objects. So something like, let's say, smaller than 10 meters, for example, yeah, or maybe over 50 meters. And we will see or try to understand when these objects are observable, or how many of these objects are observable. Only a percent of the whole time, only or less, yeah, maybe 0.0001%, I don't know. So we will compute this and answer this question, yeah, to see where, when, and where are these objects even observable. So is it advantageous to look for asteroids with a very small phase angle, so they are illuminated at 100%, or somewhere else? This is something that needs to be answered to see how we could theoretically close this gap. But the second question is also, what about the other ones? Yeah, for example, we have here NEO with 100 meter. Remember the NEO of Chelyabinsk that had a size of, I don't know, a few tens of meters. I think it was rather small, right? I already forgot its size. Somewhere here. It also already caused it had some devastating results, yeah, with the shock wave and exploding and shattered windows and so on. People were injured. Luckily, nobody was killed. And the question is, we need also to find these objects, and do we know all of them? Yeah, so it's very likely that very large objects like Ganymed, 30 kilometers, that we have observed the larger ones, but maybe there's also an observation bias for smaller ones, right? So if we assume, again, a polynomial distribution or something like that, in a logarithmic plot, the cumulative distribution should describe something like a straight line. So something that we did already for our comet part. So I will provide the link to the comet video in the description, because these things are really similar to the NEOs. I mean, they're also minor bodies, just without any activity. So let's here in the next cell, in cell number, is it now 4, 5, 6, 7? Okay, 7 was right. In cell number 10, we can now compute the cumulative distribution, but we will take not the size, but the absolute magnitude here in the very first row between 10 and 30 Mach. So yeah, just ranging it down, and then we do a logarithmic plot on the y-axis. So let's have a look how this looks like. And here you see we have here small NEO absolute magnitude values, so here on the left side, and they correspond to a larger NEO. So here we have a few kilometers or very large NEOs of a few hundreds of meters. And now let's assume that we observed all of them already. So this is our first idea, so our first requirement. We think we observed everything in this range. Now the second thing is that we say, okay, the distribution should be a polynomial distribution or something like that. So in our case here, this should describe a straight line. Again, small reference to the comet video, which means that here, this cumulative distribution should go up here. So we have a huge gap between the known NEOs of smaller sizes and the theoretical expectation. Is this the theoretical expectation? Well, there are already models. We will work with the models also in the future. But it's very, very, very likely that this very simple model could describe the theoretical expectation or the real world distribution. Because why should this distribution have a small slope change, right? And again, smaller objects are way more difficult to observe than larger ones, apparently, because they are simply brighter. So this is the task for our future to answer this thing. And now we see the size distribution and know now the fact that, okay, there is a bias and we have to find a strategy to fight this bias, to observe and get more of these NEOs. So guys, in the next video, so now a small summary and outlook. In the next video, we will take a look at the orbital distribution of NEOs. So how are they distributed? Yeah, just there will be no larger major observations or ideas. We will just take a look at them. The scripts we create there will also be reused when we use the theoretical expectation, because maybe there is a bias between theory and observation for orbital elements as well. Who knows? And then we have also to answer the question why. But this is something we will do next time. So again, some very easy plotting to get a feeling. I mean, it's summer time now. As I said, I will provide a scripting video now only every 2 weeks until autumn or so. So let's keep it a little bit more relaxed now and doing some interesting scientific insights. And then later this year, we will then, do more and more advanced stuff with modeling of a telescope, modeling the theoretical distribution of NEOs, and so on. Until then, I wish you happy coding. Thanks again. And if you would like to give me some feedback on this small science videos I provide, then please let me know. So the last video, I think, was not received that well, but I would like to continue and improve it. So any ideas are appreciated. And until then, enjoy and see you next time.